Welcome to this lecture series in real analysis. Last time we looked at the notion of a sequence of functions and what it means to say that a sequence of functions is pointwise convergent, right? And we saw that the notion of pointwise convergence is not strong enough in the sense that it may not preserve interesting properties like continuity under the limit. We discussed all of this in detail, so I'm not going to repeat any of it. And in this lecture, we'll discuss a stronger notion of convergence which does preserve important properties like continuity, etc. All right, so here are some problems, or here is one problem to further illustrate the weakness of pointwise convergence. We saw the weakness of pointwise convergence in terms of continuity. Here, the same weakness is illustrated in terms of the value of the integral of the function. So it's an important exercise. And with that, let us proceed. Okay, so what is uniform convergence? So we start with, again, a sequence of functions on a set S of reals. So it goes without saying that this is a subset of reals. Okay. We say this sequence converges uniformly to a function f with the same domain, obviously, if I'll write it down, but let me illustrate or explain the definition via picture. So we say the sequence converges uniformly to a function f if we first draw the graph of f. So suppose, so to illustrate, I'll assume that S is this unit interval. So this S is this unit interval, and suppose the graph of f looks something like this. Let me also draw a vertical line, otherwise I'll go crazy. Say that is the graph of the function f, and I'll just write an f here. Okay, so what are we trying to capture? We are trying to capture, when we say that the sequence converges uniformly to the function f, what we want to say is the following. We want to say that whenever we make the epsilon band about the function f, so this is a band of thickness epsilon. So this is epsilon and that is epsilon. So let me not mark it in the figure, but let me just say it. So this is epsilon and that is epsilon. This is epsilon, that is epsilon. So for each x, just locate the point on the graph of the function, go epsilon above and epsilon below, and that is the width, that is the kind of the neighborhood of the function corresponding to the point x. You do it for every point in the domain, you get this you get the roof and the base, and within everything between that is the epsilon band about the graph of the function f. Okay, so you make this epsilon band. What we demand from uniform convergence is that for little and large enough, any fn should be living inside this band. So if little n is large enough, then the graph of fn will live inside this band. So fix an epsilon, make the epsilon band about f, then for each large enough little n, the graph of fn will stay within this epsilon band. That is what we want to define as uniform convergence. So writing that in symbols, for all epsilon greater than 0, this supremum is less than epsilon ultimately. Right? So whatever I said in terms of pictures, I just wrote down in symbols. And why is this called uniform convergence? Well, this estimate that fn and f are less than epsilon apart at the point x is not depending on the choice of x. For all x, the same estimate works. This is not true for pointwise convergence. If you go back to the previous lecture, you will see that, one should see, I encourage you to pause the video and think about those examples again. You will see that pointwise convergence only asks for these estimates, one for each x. Once you fix an x, then you can find large enough n such that this estimate holds. That's the definition of pointwise convergence. But here we are saying that no matter what x you pick, the same epsilon works for this estimate. So I encourage you to pause the video, think about this definition, the difference between the face value of the definition of uniform convergence and pointwise convergence. Okay, so I'll leave it at that. And now let's note, or maybe I'll just mention, that if fn converges uniformly to a function f, if fn converges uniformly, then fn converges pointwise. And this is a very simple exercise, so this is marked as such. And the interesting fact is that this is actually a strictly stronger notion than pointwise convergence. Well, that is not surprising. But the interesting fact is that it does preserve the kind of things we want to preserve. So this is not something that we will discuss in this lecture, but let me mention here that uniform limit of continuous functions is continuous, which is a shorthand for saying that if we have a sequence of continuous functions converging uniformly to some function f, then the function f is also continuous. Okay? But this is the topic of probably the next lecture, not this lecture. In this lecture, we just want to understand uniform convergence well. Okay. So let's take a few examples. So define fn for each positive integer n, define fn from the unit interval to the real numbers as follows. So fn x is n upon x plus n for all x in the domain. So that's the definition of fnx. Let's try to plot it. So what about f1? If we want to plot the graph of f1, what does it look like? It is just this function 1 upon 1 plus x, which at x equals to 1 takes the value half, and at x equals to 0 takes the value 1, and it kind of decreases like this. So that's f1. What about f2? f2 looks something like that. This is f2. Right, that is f2x. So at x equals 0, it takes the value 1. So at x equals to 0, it is here. But at x equals to 1, it is 2 by 3. So it is a little bit above half. So it would look something like this. Let me draw everything again. So this is f1, then f2, and then similarly f3 would be something like that. And it will go on like that. So f1, f2, f3, and so on, ... Very simple to plot that. And we want to say that this converges uniformly. Converges uniformly to what? To the constant function 1. To the constant function 1, which I denote like this. This is the constant function 1. And it should be clear from the picture itself. We will prove it, but it should be clear from the picture. If I take the constant function 1, make the epsilon band about it. For large enough n, the graph of fn will be sitting inside this epsilon band. So that should be visually convincing, but here is the proof. So just consider this difference, right? This is by definition of fn equal to that, which is equal to this, which is at most 1 upon x plus n. I may put absolute value, may not, doesn't matter, everything is non-negative. And this is at most 1 upon n. So the estimate is not depending on x, and if n is large enough, this will be as small as we please. So that proves uniform convergence to the constant function 1. Very simple. Okay, now define this function. Note that the domain is different, but the description will be the same. The description is same as the previous one. F and x is n upon x plus n for all x non-negative. So that's Fn, and let's try to again plot it. So it would look something like this. That's F1 dies down to 0 as the input grows to infinity. Same for F2. F2 also dies down to 0, but it will always live above F1. Same for F3. Everything dies down to 0. F1, F2, F3, and so on. Now, we want to say that this sequence is not uniformly convergent. So even though the description of the functions in this example and the previous one are the same, here you have uniform convergence, while here you do not have uniform convergence. So the domain matters is all I'm saying. The description is one thing, but a function is not merely its description. It is also the range of inputs it can take, right? So first of all, we need to show that it is not uniformly convergent. Were it uniformly convergent, what could it possibly converge to? Well, to its pointwise limit. This function is pointwise convergent. So note that, in order to prove that it is not uniformly convergent, first we note that this sequence is pointwise convergent. Converges pointwise to the constant function 1. Right? Why is that? Because fix in x as n approaches infinity, this approaches 1. Right? Once you fix an x, as n approaches infinity, you get f1x, f2x, f3x. As you grow larger and larger, you will be converging to 1. That's very clear from the description. So it does converge pointwise to the function 1. Therefore, if this function were uniformly convergent, it would be uniformly converging to 1. There is nothing else that it can converge uniformly to. Right? If the function converges uniformly to something, if fn converges uniformly to something, call it f, it also converges pointwise to f. But we know it converges pointwise to the constant function 1. So, if we assume that this is uniformly convergent, then it is uniformly converging to the constant function 1. Okay, so why is it that it cannot converge uniformly to the constant function 1? Well, suppose I draw the graph of the constant function 1, which looks like that, just the horizontal line. Make the epsilon band about it. So I make the epsilon band, fix an epsilon and make the epsilon band. And it is encroaching upon my writing. Yeah, hopefully that's fine. So I've made the epsilon band about the constant function 1. And now just note that no matter what x you pick, there is some n large enough. The reverse. We want to show that there is no n large enough such that this thing, where f is the constant function 1, so we want to show that there is no n large enough such that this thing is less than epsilon. So fix an n, no matter what n you fix. If you pick x large enough, x big enough, that estimate will fail. So maybe I'll be even more detailed. What do we want to check? So we have this fnx minus 1 and the absolute value. if this were true, if suppose the uniform convergence held, then this supremum would be less than epsilon ultimately. Right? Uniform convergence exactly means that this happens ultimately for each epsilon. But what does this mean? By definition of the functions, this says that n upon x plus n minus 1 is less than epsilon ultimately, which is same as saying that this supremum x upon x plus n is less than epsilon ultimately. Yeah. Right? But what is this supremum? The supremum is 1. Fix an n. This supremum is 1. So it cannot be less than epsilon ultimately over n. So that's a formal proof. But it should be much more clear from the picture, intuitively clear from the picture, and whatever we said earlier. So anyway, I just wanted to illustrate that uniform convergence is sensitive to the domain and not the description only. And yeah, with that, just let's see one little fact, which is called the Cauchy criterion for uniform convergence. Just like we have Cauchy criterion for convergence of a sequence of real numbers, we have a Cauchy criterion for uniform convergence of a sequence of functions. So we have a sequence of functions defined on some domain of real numbers. Then this sequence converges uniformly to some function f, if and only if, I'm going to write down if and only if, for each epsilon greater than 0, there is a large enough n such that whenever n and m are at least that large enough number, we have this supremum is less than epsilon. So we have an intrinsic characterization of uniform convergence. We do not need to ask. So what am I trying to say? I'm trying to say that the limiting function is nowhere seen in this statement. Whether a given sequence of functions converges uniformly or not is not contingent upon what it uniformly converges to or anything. You can just look at the given sequence and should be able to decide if it converges uniformly to something or not. Just like given a sequence of real numbers, we can ask whether or not it converges. You can also ask whether or not it converges to a given point x, but you can also ask whether or not the given sequence converges at all. Right? Similarly here, you can ask whether or not a given sequence of functions converges uniformly. What it converges uniformly to is a different question. Right? So this is basically you could have guessed this criterion, nothing out of the ordinary here. So let me do one direction of it. This should be left as an exercise at this point, but maybe let me do one direction of it. So suppose the given sequence converges uniformly. Suppose this converges to some function f uniformly. If it converges uniformly, it is going to converge to some function uniformly. Call that function f. Then we want to show this pink thing. Then we want to show this whole thing. So fix epsilon greater than 0. By uniform convergence, we know. So by uniform convergence, we know that this supremum, I'll write epsilon by 2 ultimately. Right? I can write epsilon by 2, which is to say that there exists some capital N such that whenever n is at least capital N, we have this is less than epsilon by 2. All I did was I just expanded the meaning of ultimately. So therefore, whenever we choose M and N, both at least capital N, we have this supremum less than, and this is a consequence of triangle inequality, we have this, but both of these are at most epsilon by 2. Because M is at least capital N and N is at least capital N, by definition of capital N, they are both less than epsilon by 2. And hence, the whole thing, this thing is less than epsilon. So very, very straightforward deduction. So if we have uniform convergence, the pink thing holds. And for the converse, assume that the pink thing holds. Then for each x, this sequence is a convergent sequence by Cauchy's criterion of convergence. For each x, if we fix an x, then since this supremum is less than epsilon for large enough values of n and m, this particular thing is also less than epsilon for large enough values of n and m. Just fix an x, this will be less than epsilon. So this sequence is, this sequence for each x is a convergent sequence. Therefore, the sequence of functions is at least pointwise convergent. Immediate from this pink thing is that this sequence of functions is pointwise convergent. So we can define f as the limit, the pointwise limit of the given sequence of functions, and then argue using this condition that this is actually a uniformly convergent sequence, converging uniformly to the pointwise limit. That's all. And a very straightforward deduction can be given there. So yeah, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.